This theorem that the dimension of Bernoulli convolution is what it should be, provided there are no exact overlaps. And the last bit in this proof is the following. So for lambda in 1/2 if it is algebraic, and it happens to be that the dimension of nu lambda is strictly less than 1, then we want to conclude from this that some control on the Mahler measure. So this is what I'm going to explain in this lecture. And first I remind you that this is the Bernoulli convolution is the law of the random variable sum n goes from 0 to infinity plus minus lambda to the n. And this guy is equal to the product of the leading coefficient of the minimal polynomial of lambda times the maximum of 1 and the absolute value of each conjugate of lambda, where p of x equals AD times x minus lambda j is the minimal polynomial of lambda. So maybe I should have mentioned last time, if you haven't seen this quantity before, there is a good way to think about it. So for lambda there is a minimal polynomial, and this is for the minimal polynomial there is a matrix with integer coefficients, the companion matrix, and this will give you a total automorphism, and the entropy of this total automorphism will be the logarithm of the Mahler measure. So you can think about it that way. Okay, so I want to explain to you how with this information that the dimension of the Bernoulli convolution is less than 1, you can control this sort of complexity of the algebraic number lambda. And so first of all, I need to give you another definition, which is Garcia entropy. So let lambda be an algebraic number and then the Garcia entropy is denoted by h of lambda, and it is defined as the limit as n goes to infinity 1 over n times the Shannon entropy of the truncation of that random variable. So n goes from, okay, so there will be too many n's, so let's this be j. J goes from 0 to n minus 1 plus minus lambda to the j. Okay, so this is another way to measure the complexity of this algebraic number lambda, which is more closer to our problem. And so the reason I introduced this definition is because there is a result by Hochmann which is something else that can be deduced from the main result in this paper of Hochmann, which started this big development. It says the following: if lambda so it's an algebraic number in 0, 1, then the dimension of the Bernoulli convolution is equal to the minimum of the Garcia entropy divided by log lambda to the minus 1 and 1. Okay, so let me add a few remarks about this. So the interesting case is when you have exact overlaps, and if you have exact overlaps, then it means that you can write your Bernoulli convolution as a self-similar measure with respect to another iterated function system. And if you write down the formula that the conjecture would predict based on that iterated function system, then you can get another number. And if you think about it for a moment, then you can realize that this quantity that you see here is the infimum of all possible expressions of that quantity that appear in that conjecture. Okay, so this is quite natural, and in fact, so the proof of this is very similar to what you have seen yesterday. Okay, so basically this means that if I know that the dimension of nu lambda is less than 1, I get control on the Garcia entropy. Okay, so now how can I relate Garcia entropy to Euler measure? So this was done by me and Emmanuel Briard. And yeah, so it says that for lambda algebraic, we have that the Garcia entropy of lambda is bounded above by the minimum of the logarithm of the Euler measure and the logarithm of 2, and it is also lower bounded by 0.4 times the same thing. Okay, so this by itself is not enough for us to conclude, but this was our original result. But if you look at the proof, then you will see that you can also conclude the following, that for every epsilon positive, there is some constant such that if the Garcia entropy is less than 1 minus epsilon, then the Euler measure is less than this constant. Okay, so the upper bound in this theorem is basically trivial. So with some very simple number theory, you can show that the growth rate of the possible points that this random variable can take will be Mahler measured to the n. And of course, it's also at most 2 to the n. So this will just give you the upper bound. What is more tricky to do is the lower bound. This is what I want to talk about now. So, okay, so the proof relies on entropies of similar kind of quantities that we used last time, but this time we use a different kind of smoothing. So let me introduce this. Okay, so let X be a random vector. And so in Rd, and let A be a matrix in GL dr. So then we write for the entropy of X at the scale given by this matrix A the following. So it will be the differential entropy of the random variable X plus A times G minus the differential entropy of G, where G is the standard Gaussian, which is independent of X. And now H of something stands for differential entropy. So what does that mean? If F is the density of X, then the differential entropy of X is defined as the integral on Rd of F times log F dx. Okay, so perhaps somewhat counterintuitively, this is a quantity that can be negative. But this difference is always non-negative. Okay, so how is this connected to the quantity that I used last time? So last time I used a quantity which was only in one dimension, and it was entropy of something at a scale s. And so I didn't tell you this last time, but another way to define this quantity would be to compute the differential entropy of x plus s times I minus the entropy of s times I. Oh, sorry. Where I is uniformly distributed on 0, 1 and independent of x. So if you remember the definition from last time and you do a quick calculation in your head, then you can see that, yeah, maybe that was too brutal. You can see that, that you can define it this way. So the difference with the quantity that I'm using this time is that I'm using Gaussian smoothing. And this is absolutely critical for this proof. So this is really what makes it work. So let me tell you a little bit about some properties of this quantity. Okay, so if x is a discrete random variable, then if you look at the entropy of it at any scale, then it will be at least 0, and it is at most the Shannon entropy of x. So I hope my notation is not too confusing. If I have a random variable which is discrete, then if I write down h of x, then I mean Shannon entropy. If the random variable has the density, then I mean differential entropy. Okay, so this is quite something that you would expect if my definition makes any sense, and it's not too surprising that it was. Perhaps something which is a bit more surprising at first sight is that suppose that A1 and A2 are in GLDR, and with the property that A1 transpose of x is less than or equal to A2 transpose of x for all x in RD, and let x1 and x2 be independent random variables. Then the entropy, the conditional entropy, which I haven't yet defined, but I will write down in a minute, probably you can guess anyway, so the conditional entropy of the sum of x1 and x2 between the scales A1 and A2 is always at least the conditional entropy of either of these summands between the same scales. And it is always at most the sum of the two entropies. Okay, so I haven't yet defined. So let me just write it down so that it's on the board. So the conditional entropy between two scales is just formally defined as last time, the difference between the entropy at scale 1 and at scale A2. Okay, so this inequality is so again this is not something that should be really surprising, that entropy can only increase if you do a convolution, because convolution is supposed to smooth. But there is no loss in this inequality, no constants, nothing. And this is very important, because what we are going to do is that we want to have estimates which are true in any dimension, and this is very important for us. So in this talk, this will be enough for me. I never want to gain anything. I just don't want to lose. Okay, so I'm not going to prove this, but just to explain what's happening here. If you have this condition, then it will ensure that if you look at the Gaussian, which is A1 times G, you can convolve it with something and get A2 times G. So that's the critical property here. So
that is true because it's a Gaussian.
Say again?
That is true because it is a Gaussian.
And because of this property. So this is equivalent to saying that A1 of the unit ball is contained inside A2 of the unit ball. Okay, so this is all I need about these guys. Maybe let me try to put this a little bit higher. And yeah, so now we are almost getting to the proof. So how am I going to use this? So let A be a matrix whose eigenvalues are the Galois conjugates of lambda with modulus less than 1. So what are Galois conjugates? These are just the other roots of the minimal polynomial. And so one small remark is that if lambda is an algebraic number such that the minimal polynomial has a leading coefficient which is not 1, then it immediately implies that you don't have exact overlaps, and then the dimension of the corresponding Bernoulli convolution will be 1. So it is safe to assume that the leading coefficient is 1. And I'm going to do that from now on. Okay, so so we have this, and then and then we can observe the following, that for any vector in Rd, we have that the Shannon entropy of the sum of j goes from 0 to n minus 1 plus minus lambda to the j is equal to the Shannon entropy of the random vector sum of j goes from 0 to n minus 1 plus minus a to the j x. So why is that? You can diagonalize the matrix in a basis of eigenvectors, and so whenever 2 points for some sequences of plus or minuses collides in here, it will also collide for any other eigenvalue of the matrix A, because the other eigenvalues are Galois conjugates. So they satisfy the same polynomial equations as lambda. So this allows me to transfer my problem from here to here. So now I have a d-dimensional problem, which is not immediately clear why it makes life better, but at least this contains all the eigenvalues, so I have a chance of bringing in the Mahler measure. Okay, so this will be an important random variable for us, so I introduce some notation, and the law of this will be, or do I want law or no? Okay, so I just write, for this I write x a little x and 0 n minus 1. So in general, if I write here m and n, then you can figure out that the summation is going from m to n. So I'm not going to write it down. Okay, so what can we do with this? So the first observation is that if our matrix has norm less than 1, then the Garcia entropy h of lambda is greater than or equal to the limit as n goes to infinity of 1 over n, the conditional entropy of x a x 0 infinity between the scales a to the L and identity. So this should not come as a surprise, because the effect of looking at scale a to the L, it roughly means that you cannot see anything in this series defining this random variable which has scale less than a to the L. So anything beyond the nth term, and the Shannon entropy of that guy is just what appears in the definition of Garcia entropy, and we have seen that the Shannon entropy is an upper bound on the entropy at a scale. So, say again?
What do you assume about small peaks?
That can be anything. So this is for, well, probably not zero. Well, I guess it's this is true for x equals 0 also, but it's just trivial. This one requires that it's not 0. Okay, so maybe I write down the proof of this.
Can I ask a question?
Yep.
I actually can't read that. That says x, a, k, 0. Is that n minus 1 there? Or
This one?
is that infinity?
That's infinity, yes. Okay, so let's write down the proof of this. So, okay, so I have this entropy appearing in the definition of Garcia entropy. So when I divide this by n, it will converge to the Garcia entropy. And as I have already remarked, this is equal to the conditional entropy of xa x0 L minus 1 at scale a to the, sorry, just channel entropy so far, and this is greater than or equal to the entropy of the same thing as at a scale, which I can pick whatever I like, and I will pick a to the L.
So why did it's n?
Yes, sorry, I have. I started to write n, and there are L's in my notes, and then I just maybe I shouldn't use my notes. Okay, so this is equal to so I write it down, then and I explain. Okay, so what did I do here? What did I do here? So this random variable is just a scaled version of that random variable, and I also scaled the scale with the same amount. So there is a scaling formula for these quantities, which is similar to the one that I used last time. So this time I didn't write down, but basically it just says that. Maybe let me write it here, that the entropy of a random variable between scales A1 and A2 is equal to the entropy of A times X at the scale A1 conditioned on A2. So that's what I'm using here. So I just subtracted the same thing that I did, and so what I wrote there is that the entropy of the sum of two independent random variables is bounded above by the sum of the two entropies. So I can write now that this is greater than or equal to the entropy of xa x 0 n at scale a to the n, conditioned on ID. And yes, so now if you take the limit n goes to infinity, then you and divide by n. Before doing that, then you get what this lemma claims. Okay, so far I didn't do much.
Sorry, why do we know that there is a Galois conjugate with notables less than 1?
If there is no, if lambda is the only one, then lambda is the only one. Then this is just a one-dimensional thing that I'm doing. Yes, including lambda. Yes. Okay, so what am I doing next? So the second lemma is that h sub lambda is greater than or equal to the entropy of the same random vector between the scales A and identity. So maybe I don't write down the proof of this. This is the same standard argument that you do in entropy theory. So you can just write this as a telescopic sum for all the scales and realize that this guy is the smallest among the terms. Okay, so we got to this point, and so far whatever we didn't make much losses. So you can actually, if you think a little bit about this, then with the correct choice of the vector, you can kind of make sure that this, so far you didn't lose much. But we also didn't gain much, because if you look at this object here, this is really, really frightening. It lives in some d-dimensional space, and it has some sort of really complicated structure, so it's not clear how you could estimate such a complicated beast. And again, let me stress that somehow the game here is that you want to do something which doesn't depend on the dimension. Okay, so at this stage we do something drastic, and it's simply that here we throw away everything except for one term. Okay, so this holds because convolution can only increase entropy. And now this is an object that I'm much more hopeful that we can estimate, and then we hope that what we did here, it didn't lose too much information, and it turns out that we will be lucky. Okay, so we still have a lot of freedom. We can choose the vector whatever we want. We can choose the matrix subject to the constraint that it has to have norm less than 1, and it also, yeah, actually it even can have norm 1. That's still fine, which will be important for me in a minute. And the eigenvalues are also prescribed. Okay, so we can introduce a little bit more flexibility. So for any orthogonal matrices, UV in OD, we have h sub lambda is greater than or equal to the entropy of plus minus ux uav identity. Okay, so why is that? Well, the only restriction that I have on A is that okay, so there are two restrictions. That the norm has to be less than or equal to 1, and I have prescribed eigenvalues. So it means that if I conjugate it with an orthogonal matrix, that I'm okay. So I could put here V inverse A V. Now I can also multiply everything with another orthogonal matrix. So I can multiply with U from here, and with U from here, and then I should have here U. But this is standard Gaussian, so if you rotate it, you don't do anything. So you can leave their identity. And because I have total freedom to choose X, let me just forget about this U also. Okay, so now what is my restriction? So I want the norm to be less than or equal to 1, and I have prescribed eigenvalues for this matrix. And there is result in linear algebra, which is called Horn's theorem. And so it implies that there is a matrix A with prescribed eigenvalues lambda 1, etc. lambda d, which are all less than 1 in absolute value. And with singular values which are 1, 1, 1, etc., 1, and at the end you get the product of all these guys in absolute value. Okay, and now this looks very promising, because this is, in our case, this will be equal to the Mahler measure of lambda to the -1. So the Mahler measure was defined as the product of the absolute values of the roots outside the unit circle. But if you take the product of all the roots, then, well, okay, so you can assume that the leading coefficient and the constant term are also plus minus 1 in this business, and then the product of all the Galois conjugates will be plus or minus 1. So if you just take the product of those which have absolute value less than 1, you get 1 over the Mahler measure. And so this means that I can go a bit further and do the following, that h of lambda is greater than or equal to the entropy of plus minus x, and I can put there a diagonal matrix with entries which are all 1 and the Mahler measure of lambda to the -1, and then this is conditioned on scale identity. And I still have total freedom to choose x, and it's not too surprising that I will take this to be the last coordinate vector. And if I do that, then basically nothing is happening in the first d-1 coordinate, so I can just integrate them out. And so what am I left with? Is that this is greater than or equal to the entropy of plus minus t, and now this is in R. Yeah, so I take actually t times the this unit vector, and at scale m lambda to the -1, scale 1. Okay, so now this is not the notation that I used last time. I'm still using Gaussian smoothing, of course. And now this is a one-dimensional problem. And the only thing it knows about lambda is its Mahler measure. So it means that I'm in a really good shape. And this is basically just a calculus exercise to optimize this for t. And then you get a lower bound on the Garcia entropy in terms of the Mahler measure. And if you analyze this problem, then you get the claims in this theorem that I mentioned in the beginning. So is it correct that I still have a few minutes?
Yeah, we can.
Okay. So this basically completes the proof, and I just want to add a few remarks. So what are the things that we don't know? So we don't have the same theorem for self-similar measures other than Bernoulli convolutions. So this exact overlap conjecture, this is the first instance where it is proved, and the other cases are pretty much open, though I'm hopeful that the methods will help. But even for Bernoulli convolution, our understanding is far from complete. So we are doing now quite well for dimension, and we are also doing okay for absolute continuity. This is what Pablo talked about before, and we have some additional results. But if you want to say something more, you would like to say that it's not only absolute continuous, but the density is smooth, so maybe it has some number of derivatives. Then basically we are roughly at the same point where we were in 1940. So essentially no progress. So even you can ask questions about dimension. So now what remains is to understand the dimension for algebraic parameters. And it is basically reduced to the problem of estimating the Garcia entropy. And if you give well, maybe not me, but someone who knows how to use a computer, a number with a minimal polynomial, then you can approximate this Garcia entropy with arbitrary precision numerically. And so there is an algorithm to do this. Algorithm for approximating h of lambda. So this was done by Akiyama, Feng, Kempton, and Persson. And then there were some developments by Feng and Feng, who use other algorithms to get some things which are very precise. So just to illustrate the kind of things that they can do. So let lambda naught be a number which is approximately 0.5283, be the root of the polynomial x cubed minus x plus x squared plus x minus 1. And then the dimension of new lambda naught is equal to 0.9804093193 plus minus 10 to the minus 11. And they also proved that for all lambda in 1/2 we have the dimension of the Bernoulli convolution is at least 0.980368, and the minimum for nu sub lambda is attained in the interval lambda naught plus or minus 10 to the minus 4. So, at least to me, these are pretty impressive. So the actual numbers are not that important, but I think the precision is quite striking. So at least the strongest suggests that this is probably the worst guy. But these things are very, very far from being proved. And yeah, so you could even conjecture that exactly what are the lambdas where the dimension is less than 1. But these things, proving something theoretically here is still very much challenging. Okay, so now I'm definitely over time, so I stop here. Thanks.
Thank you. Are there any final questions? No, thank you again.
Thank you.